All right, so today we'll talk about a lot of the things that we'll talk about today will be in chapter 2 of Miesler and Tar. As usual, I'll talk about some things that aren't in the chapter, and I also will skip over some things that are in the chapter. But the bulk of what we'll talk about today is from chapter 2 of Miesler and Tar, and we'll talk about atomic structure. So what we have here is the What we have here was an unexplained phenomenon from right around 1900 uh, when hydrogen gas was heated up in one of these tubes, and then the light that's generated from heating the gas in the tube was sent through a prism. The light gave a very discrete spectrum. Most of the things that they were used to from classical physics, this was not the case. They expected to split and see the rainbow. Okay, just like if you were to go outside and take some light and shine it through a prism, you get an entire rainbow. Instead, most of it was dark, with the exception of these four lines. These lines could be really precisely determined in the spectrum. Take a little bit further. So this is what we looked at. This is the hydrogen emission spectrum. Here's the same lines that we saw just a minute ago. And an interesting thing here is if you take and you shine white light, which has all the colors in it, something like sunlight, on a hydrogen sample, it would absorb these same bands. Okay, so they knew that something fundamentally to do with the element itself was going on here, and so they investigated this further. The Bohr model was the first one that could was the first explanation of what was going on here. Bohr said that we have a positively charged nucleus, we have a negatively charged electron going around. We have only two types of energy here. The electron is moving, so it has kinetic energy, and the electron is attracted to the nucleus, so it has potential energy. And what he predicted was there were only certain stable orbits the electron could be in. So it could be in, if we think about the planets, it could have a Mercury orbit, a Venus orbit, an Earth orbit, but it wouldn't exist in the in-between spaces. It only could find one of those stable orbits to exist in. One of the most important things I want you guys to get from this is all of these energies that we calculate are negative. So anything stable, starting here with a hydrogen atom, but no matter what it was, if we were doing any sort of computational chemistry, the values will end up being negative for a stable species. And so here's the first few energies for the hydrogen atom. So this is the ground state. This is the most stable state. And this is the most negative energy. If we go to n equals 2 here, it's still negative, of course, but it is less negative. Say, so the n equal 2 state is less stable than the n equals 1 state. And then n equals 3 here is just barely negative, but it's still negative. And so this is the least stable state. So as we take this electron and we move it further and further from the nucleus, it becomes less and less stable. The atom becomes less and less stable. Here's just throwing a whole bunch of that together. So there was a big party at the time about this. So the first set of lines were predicted really accurately. But also, and those were the visible, the ones that we had just looked at, these four lines are in the visible part of the spectrum. These were the first to be noticed, of course, because you can actually see those with the naked eye. People were really excited, though. You could also predict using the same equation that Bohr came up with, this Lyman series, which you can't see, it's in the ultraviolet, and the Pachin series, which is in the infrared. And it predicted these all really, really nicely. And it's a really simple equation here where we take a constant, so here's the constant multiplied by the difference of the fractions. And this is the these n values are right here. So n equal for the low level, so this is n for the low level, and then n for the high level. If we put those numbers in, we predict this exactly to match the experiment. Well, it wasn't so easy when we moved to anything else, though. So helium's still super simple. It's got a +2 charge in its nucleus. We've got 2 electrons now. If we go and try to use the same equation and put in now double the nuclear charge, and for the n equal 1 level, we predict the energy to be minus 54.4 4 electron volts, and the actual energy is minus 24.6 electron volts. And we'll talk about this more in class, but what we've neglected, what the Bohr model neglected, was the repulsion between the two electrons. So it sees the kinetic energy of the electrons from moving, it sees the attraction to the nucleus, but it's missing out on the fact that there's a repulsion between the two electrons. You don't have to worry about this too much. We'll talk about this in more detail. You can look at the slide later if you want to. This is Schrodinger's wave equation. This is most of the things that we do computationally now still are based on this, where we have an equation that represents the probability of finding an electron. We work on it with some operators, we get energies out. Again, the energies are still negative. The more important thing, we'll talk about this in the subsequent slides, we have these three numbers that come out of this equation. N, the principal quantum number, and it can have values of 1, 2, 3, 4, all the way up to infinity. L, the angular momentum quantum number, will be 0, 1, 2, all the way up to n minus 1. And M sub L, which is the magnetic quantum number, and it can have values from minus L all the way up to plus L, going through 0. What came out of this immediately? So Heisenberg was the one to actually interpret this physically, what this means. So before, we were thinking about orbits, so just like planets going around the sun. Now, however, we're talking about orbitals. And so this is no longer, Bohr was thinking about a two-dimensional shape, a circle. This is a sphere. And now we talk about probabilities instead. So all the type of atomic and molecular orbitals that you're used to looking at, those are actually probabilities. And here it's been chosen, this circle, there's an 80% probability of finding an electron in that circle. Okay, and for our s orbitals, which are the only ones we've talked about so far, this is going to be a spherical distribution of the electron. All right, well, here's some of the stuff that I will need you guys to know. So any valid combination of n, l, and m sub l defines a unique orbital. The orbitals are named after the quantum numbers. And in particular, L gets names. So the L quantum number, if L equals 0, it's an s orbital. L equals 1 is a p orbital. L equals 2 is a d orbital. And L equals 3 is an f orbital. Well, you may remember from general chemistry, the Schrodinger equation requires 3 quantum numbers, but there's 4 when we go through and talk about it. This Stern-Gerlach experiment showed that the electrons also had something that can be referred to as intrinsic spin. So they can align themselves with or against the electron, with or against the magnetic field. If you impose a magnetic field, here's a north pole and the south pole, you split these exactly 50-50, 50% going up, 50% going down. All right, well, here's the thing that I will need you guys to retain for when we get to have an exam, is basically this slide. You need to have all of this committed to memory. So N is the principal quantum number, its name. You need to know its name. You need to know what its values are. So it starts at 1, not at 0. It starts at 1 and goes 1, 2, 3, 4. It's integers all the way up to infinity. Determines most of the energy. L, the angular quantum number, it's dictated by whatever our n choice was. So it's 0, 1, 2, so it's integers again all the way up to n minus 1. It describes the shape of the orbital. Then M sub L is the magnetic quantum number. It has values up to L. So whatever our L value is here, the M sub L gets dictated by that. And so it goes from minus L all the way up to plus L. So this is an L and that's the 1. The font's not great to show that. But it is integer values from minus L through 0 up to plus L. And then the easiest one here is M sub S, and that's the spin. And an individual electron can have a spin up, so it can be plus 1/2, or it can have a spin down, which is minus 1/2. All right, here summarizes all of that. N has values from 1 to infinity, integer values. L is from 0 up to n minus 1, dictated by whatever n was here. M sub L goes from minus L through 0 to plus L, and then M sub S can have values of plus 1/2 or minus 1/2. I won't worry about this too much. I just want to mention this. This could be useful for you later in your career. So the the shading of the orbitals doesn't, the shape of the orbital is determined actually by the square of the wave function, and the square doesn't have any sign to it. Okay, when you square a positive number, it's positive. When you square a negative number, it also becomes positive. So the actual square itself doesn't have any, negative or positive value to it. This actually comes from what the wave function itself originally was. And when we talk about these, it only matters that the shading is different. So it would be exactly the same orbital if I made it be blue on top and white on the bottom. It just needs to be the wave function is a different color on top and bottom. All right, well, the shapes of some of our atomic orbitals, probably really used to seeing the 1s orbital. It's totally spherical orbital. The 3 2p orbitals have the same shape, but they point in different directions, and you'll need to know this. This is something else you'll need to commit to memory. The 2p, or any of the p's, px orbital is along the x-axis, the y orbital is along the y-axis, and the z orbital is along the z-axis. All right, and here's just a different representation of those. They're made a little bit more see-through, and this is a better physical picture that we have here. So again, you can think about this as like a time-lapse camera, and they've snapped 10,000 photos of where the electron is over time. So it's hanging out in this area, hanging out in this area. So this is 1s, 2s, 3s electron. And here's our just 2p's again, but again, it's this type that we can see through them. All right, our d orbitals, we have our 5 d orbitals, and you guys need to also know and be able to draw these on some coordinate axes if I were to provide them to you. This is our dz squared orbital, and I can tell that because this big lobe goes along the z-axis. This is dz squared. This one right here is dx squared minus y squared. I can tell that because it goes along the x-axis and along the y-axis. It goes along those axes. Okay, and here's where it gets weird. For the ones without squares, so for example, dxz, so dxz is right here. It's one of the orbitals without a square, and so it lies between the x and the z-axis. Notice it lies right between those axes. Same deal here. This one would be the yz. It lies between the y-axis and the z-axis. And this one would be the xy. It lies between the x-axis and the y-axis. Okay, so at some point I'm going to ask you, I'm going to give you some axes just like these and ask you to sketch those for me. All right, and this is what this is all going to build up to, is the fact that when we understand how, for example, here are the orbitals on oxygen and the orbitals on the hydrogen atoms, how they combine, we can understand how water then comes together. This later helps you understand mechanism a lot. All right, here's the questions for you guys today. So based on what you saw earlier, I want you to complete this table. I suggest when you work one of these tables to work each one of the rows from left to right. So look at this first value here and look at the rules and see if this is okay. If that guy's okay, move to this one. If this one's okay, move to this one. And if all three of those are okay, move to this one. If when you're going along, if you hit any value that's not okay, I would put a big X through that value, and then that means that orbital is not allowed. If any of its values are unallowed, the orbital is not allowed. However, in the cases where all 3 or 4 of the numbers are allowed, circle yes, and then name it. Okay, so you're going to give the principal quantum number as the first part of the name, and then the second part of the name is that code, SPDF 0123. All right, last two should be pretty easy for you. You guys can look through the equations and work this out. How many d orbitals are possible for n equals 6?